In this video we're going to look at the Legendre Transform in terms of differentials. That is, we're going to look at the sensitivity in effect of our Legendre Transform. So let's take for example what we have here. We've got our function x squared, which is in black. We've got the Legendre Transform, which is in blue, and you see I've drawn in the tangent to a point, so we can follow that point round the curve and we can map out the exact point on the Legendre transformed curve. Now what we're really interested in here is what happens whenever we change the value of x here just a little bit. So if we were to change this value of x just a little bit, then the value of our f of x is going to change. If the value of our f of x is going to change, then it means that the next point along in the curve will be chosen and the gradient is obviously going to change as well. So if that gradient changes, then you can see that our y-intercept is going to change as well. So if our y-intercept changes, then it means that the height of our Legendre transform changes. So we're really looking to see the sensitivity of changing this value of x and to see how this in effect will change the height of our Legendre transform. Now in this example here, it's not a particularly good example because for f of x is equal to x squared, the height here is always going to be the same as the Legendre transform height. So if I move this up and down, you'll see that the gradient and the y-intercept, the y-intercept there is always going to be this value and the equal distance from here to here is from here to here. Okay, so what we'll do is we'll change this to something else. So let's say we change it to x to the power of 8. Okay, so it's x hat 8. Now this gives us a better description of what we're interested in. So you can see here at this point here, whenever we change the value of our x by a small amount, you can see that the gradient of this black curve is going to change by a large amount. Now if the gradient changes by a large amount, it means that the intercept here is going to change by a large amount as well, which also means that the final value for our Legendre transform will be a large change. So you can see here that this function, as it heads up along further to the right, becomes very sensitive to any change in the value of our x. And that's really what we're interested in this video. So what we're going to do is we'll look at the mathematics of this, and the mathematics might appear to be a little bit contrived, but we are doing it for a particular reason. Whenever we go on in the next video and we look at extending the Legendre transform to a function of two variables, then the little bit of maths that we learn here is going to be useful to us. So let's go ahead and we'll write out what we've seen here mathematically, and we can see if we can write out mathematically the Legendre transform in terms of the differentials. So in effect, it kind of gives you the sensitivity of the Legendre transform to the original curve. Now before we go any further, we've got a nice interesting little exercise which helps to ensure that we have an intuition of what's happening here with our Legendre transform functions. Now you'll have seen the first one here and also the second one, but we're actually going to be using a third form, and this is the form we're going to look at in this video, and we're going to be using this whenever we look at the differentials. Now in order to ensure we know what we're talking about here, let's just go through an example and we'll start putting some values in. So let's say for example we start off with our function f of x is equal to x squared. So we've seen this throughout the video series so far. So we've got that function in black here, and the Legendre transform is the function in blue. Now let's put values in here for our x, and we'll work out and see that the left hand side is the same as the right hand side, and we'll ensure we understand what each of the terms is. So pick a value for x. Now in this case here we could pick any value for x, but the x here I've chosen is 1.5. So the actual a value here is just the x value. So we've got 1.5 here. So our g of x, well, what is g of 1.5? Well, the g is nothing other than the point at which the tangent at 1.5 hits the y-axis. So we go to 1.5, we go to our curve for y equals x squared, we find the gradient, or we draw the tangent line, and that's point there where it crosses the y-intercept. That is going to be our g of x. So in this case here it's going to be minus 2.25, and you see here I've noted it down here, that's this minus 2.25. So the right hand side here is going to be the value of s. Well, what is s? Well, s is the gradient of our function at that point 1.5. So we come along 1.5, we go to our function y equals x squared, and we find the gradient. In this case the gradient is a value of 3. So it's going to be 3, and I've got the 3 here, times our value of x, which is 1.5. And that's going to be minus the value f of x. So whenever x is 1.5, our f of x is going to be, well, if you go along 1.5, it's 1.5 squared, which is 2.25. So finally we're going to have the left hand side here, minus 2.5 is equal to the right hand side. Now you can see that it's not actually equal to it because the value here is minus 2.25 as opposed to over this side here it's going to be plus 2.25. But we mentioned that before when we said that the reason for this was that we wanted to represent this curve here in the positive y-axis as opposed to this negative curvature in the negative y-axis. So if we move on to the next one, instead of writing the Legendre transform here purely in terms of our original variable x, we wanted to write it in terms of our new variable s, and we said that s is related to x and that s is the gradient of our original function at that value of x. So they are what we term canonically conjugate. The value of s is related to the value of x. They're not independent variables, they are actually dependent variables. So if we pick a value for s, now we can't pick any value for s, we have to pick the value for s which is related to this x. So in this case here our x is 1.5 and it gave us the value of s which is the gradient of 3. So if we put in and work out the g of 3, well, the g of 3 is simply going to be our function here in blue at the value of 3. So we go to 3 and we're going to come up a height of 2.25. So that's going to be on the left hand side we're going to have 2.25. So the g of s is 2.25. Now the right hand side is going to be the value of s. Well, we know our s, which is our gradient, which is 3. And the value x of s. Now what is the x of s? Well, x of s is the inverse of our function s of x. So our s of x is this function here differentiated. So when we differentiate this we get our 2x, and then when we find the inverse of the 2x, that's going to be given by s upon 2. So you can always review that in a previous video if you like to go and have a look at it. So this is going to be, x of s is just going to be s upon 2. So that's just for this particular example. If you had a different function here, you would have a different value for x of s. So that's going to be s upon 2. So what is s? Well, s is our 3 divided by our value of 2, which gives us a value of 1.5. Now the next term here is going to be f of x of s. Well, what is x of s? Again, it's going to be our value of the 1.5, and the f of 1.5 is going to be, well, you go to 1.5 and the f of 1.5 is the height here, which is our 2.25. So the left hand side here is the same as the right hand side. So that does work. So now finally we're going to look at a different equation. The first equation here is in terms of our original independent variable x. The second equation here is in terms of our new independent variable, which is going to be our s. But really what we want to do, in order to jump between the different forms of the Legendre transform, we want to have our foot in both the s domain and also the x domain, and that's what this function here allows us to do. So this has got a function, g is a function of s, and it's got f, a function of x. So we've got our feet in both domains within this equation, and that's going to be handy whenever we look at, for example, extending the Legendre transform to a function of two variables. Because with a function of two variables, we've got four different ways we can represent the information, and if we're going to jump between each of those representations, it's easier to do it whenever we've got an equation which has got a foot in the s domain and also a foot in the x domain. So this is the equation we're going to use throughout the rest of this video. So let's go ahead and we'll put the values in for this, and we'll see why this here is just the same as this up here. So let's put in our value first for s. Well, we know our s is going to be a value of 3, so our g of s is going to be 2.25, so that's the 2.25. And again, the right hand side here is going to be the same as the right hand side for the top one. So again, that's just the same as this here. So we've got the left hand side is equal to our right hand side. So in here we can say that our g of x is the same as our g of s. Now we're able to say that not because the value for x and s, they're not independent of one another. We can only say that because they are actually dependent on one another. They are canonically conjugate. One is the derivative of the other. So let's continue with this function here, and we'll see how we can use this in order to start looking at the differentials. So we mentioned that we wanted to look at, in effect, the sensitivity. That is, if we change this value of x, how does the value of g change? So we have our function here, which we talked about just a minute ago, and this function here has got a foot both in the s domain via the g and also the x domain via the f. So if we were to look at a small change here, then what's going to happen is the small change in g can be written simply as dg. The small change in our function f is going to be written as our df. Now the s times x, we're going to have to use the product rule for differentiation. So what we want to do is differentiate one, multiply it by the other, and then differentiate the first, multiply it by the second. So we keep the value of s, and we find the differential, which is going to be dx, and then we keep the value x, and then we'll have our differential ds. So on the next line here, we'll keep these the same, but you note that df here, so that's your small variation in the function f, well, that's going to be nothing other than df by dx, which is just the gradient, times our distance dx. Equally, you can look at these and say I could cancel this with this and you're just left back with the df, but geometrically speaking, we can think about that as a gradient times a distance is going to give us a small value or a small change df. But you can see here as well that we already know that this value s has been defined. The value of s is the gradient of our original function f, so that's just our df by dx. So it means that this whole term here is going to cancel with this term here. So you're just going to be left with our dg is equal to x ds. Or equivalently, we could take our ds down and we just got our dg by ds is equal to x, which is correct, and we've seen that in a previous video. Now, we could have got down to this line really simply without going through these extra steps, and we'll do that just now. So if we wanted to, we could just differentiate this whole thing here with respect to s. So we would be differentiate this with respect to s, we'd simply have our dg by ds, and the right hand side, well, that's not a function of s, so we can forget about it. So when we differentiate the sx here with respect to s, we're just going to be left with the value of x. So just to be sure, that's just like saying, it'd be similar to saying d, if x was a number, so it would be, say, 5x by dx. That would just give you a value of 5. Okay, so that's in effect what we've done here. So we'll just differentiate this thing here with respect to s, and x here would just act like a constant. So when we differentiate it, we'll just be left with the constant x. So you might be wondering why we bother going through this extra bit of detail here in the mathematics, and why we don't just do the differentiation. We can jump straight to this line. Well, there's reasons for doing it like this, and whenever we go into the next video and we look at extending the Legendre transform to a function of two variables, then we're going to use a bit more mathematics along this line here, and we're going to use the results here in order to work out the same set of equations but for a function of two variables. So it's going to be handy, that's the reason for going through this, it's going to be handy for the next video. So what we've really looked at here is we've looked at what happens when we vary x, and what happens when we vary x, what happens to this value of g. So it's the sensitivity of g on x. Now we could go through the other route as well. We could look at the varying g and looking at the sensitivity on x. So let's just go and we'll do that now, and that'll be us finished. So we have the same setup here, but in this case, instead of varying this and looking at this section here, we're going to think about it in terms of varying this one and then looking at the change here. So we've got the same function here, but what I've done is I've rewritten it in terms of the f of x. So I've just taken the original function here and I've just transposed it for f of x. So again, what we can do is we can differentiate this time, but we're going to differentiate this time with respect to our value of s. So this is going to be give us our, with respect to our value x. So this is going to give us our df here. It's going to give us a value of dg here. Again, we're going to have our s dx plus x ds. And this instance here, we can leave these, and our dg, well, that'd be nothing other than our dg by ds times ds. Okay, so it's the change in g with respect to s, that's in effect a gradient, times a small distance. It's going to give you the distance at dg. But this value here, x, it can also be written as dg by ds. So this term here minus this term is going to give you a value of 0. So you're just going to be left with df is equal to s dx, and whenever we take the dx down, we'll just have our df by dx is equal to s. And we know that that's true because that's how we've always defined it. S is the gradient of the original function f, so it's going to be df by dx. Now again, we didn't need to go through this little bit of detail here in the mathematics. We could have just simply done the differentiation. So we could have differentiated this whole thing with respect to x, and we could say, well, this is not a function of x, so we can forget about it. So we're just simply differentiating this with respect to x, which again is just going to be leave us with the value of s. So we could have jumped straight from this line here down to this line, but we haven't done this, and we've added in some intermediate steps because we're going to use these steps in the next video whenever we look at the extending the Legendre transform to a function of two variables, and that's where it actually comes in use with our Hamiltonian mechanics. So that's all for this video. Thank you for listening. I'll get you in the next video. Goodbye.